Today, today we're going to discuss monotone sequences. There are many situations in which it is important to know whether a sequence converges, but the value of the limit is not relevant to the problem at hand. In this discussion, we will going to study several techniques that can be used to determine whether a sequence converges. So let's start with the terminology. So let's have the definition. So a sequence, okay, ranging from 1 to infinity is called strictly increasing if the elements, every elements in the sequence is increasing in value. And there's no such element that is congruent or the same value with another element within the sequence. It is increasing if the value of the sequence is increasing and there are some of the elements within the sequence is there are elements within the sequence is the same value with other elements. It is strictly decreasing if the value of the sequence is decreasing, okay, and it is decreasing if it is decreasing and or there are elements within the sequence is congruent to another elements. So a sequence that is either increasing or decreasing is said to be monotone, and a sequence that is strictly increasing or decreasing or strictly decreasing rather is said to be strictly monotone. Let's have an example. Okay, in this case, we are going to show what are the examples of um, different monotones. Okay, here it is strictly increasing or strictly monotone. As you can observe, in each element in the sequence is increasing, and there's no element within the sequence that is congruent or equal to another element. This example is strictly decreasing, as you can see that as the elements or as the sequence progresses, the value of each element or each sequence is decreasing also. So let's have another example. This is example of increasing but not strictly increasing. As you can see in the elements, there are elements that is the same value with another sequence, another elements within the sequence. And this is example of decreasing but not strictly decreasing. Okay, the same what happened to the fourth example, but this is in decreasing manner. And there are elements within the sequence that is congruent to another or the same value with another element. And this is neither increasing nor decreasing. As you can see, as the sequence progresses, the elements within the sequence is alternating with each other. So these are examples of different types of monotones. Okay, so let's have test for monotonicity. Okay, in this presentation, frequently one can guess whether a sequence is a monotone or strictly monotone by writing out some of the initial terms. However, to be certain that the guess is correct, one must give a precise mathematical arguments. So these are the ways, okay, to determine the monotonicity of the given sequence. So difference between successive terms and ratio of successive terms. So if the difference of the successive terms is greater than 0 or the ratio of the successive terms is greater than 1, then that is strictly increasing. If the difference of the successive terms is less than 0 or the ratio of the successive terms is less than 1, then that's strictly decreasing. If the difference of the successive terms is greater than or equal to 0, or the ratio of the successive terms is greater than or equal to 1, then that's increasing. And if the difference between the successive terms is less than or equal to 0, or the ratio of the successive terms is less than or equal to 1, then that is decreasing. Okay, so let's have an example. So use differences of successive terms to show that 1/2, 2/3, and so on to n over n plus 1 is strictly increasing sequence. The pattern of the initial term suggests that the sequence is strictly increasing. So to prove that, we have to state that, let's say, for our solution, so for our solution, uh, so let our a sub 1, a sub n rather, would be the general term, the n over n plus 1. Then the next term of the a sub n would be a n plus 1. So that means we are going to add 1 in the sequence. So to add 1 here, then we are going to have n plus 1 all over n plus 1 plus 1 because we're going to add 1. So that means we have uh, n plus 1 over n plus 2. Okay, now, since in the instruction that we are going to use the difference, then we could have our uh, a sub n plus 1 minus uh, a sub n, which would be equal to n plus 1 minus n, uh, all over rather, n plus 2 minus n over n plus 1. Okay, in this case, uh, we have uh, n squared plus 2n plus 1 minus n squared minus 2n all over the product of the denominator. So that would be n squared uh, plus 3n plus 2. Okay, so simplifying, okay, simplifying, we have uh, this is cancelled out. What we have 1 all over n squared plus 3n plus 2. Or you could also write that one as 1 over, because the denominator is, we can write it in the factored form. So that is n plus 2 times n plus 1. Now, take note that in this case, our n should be greater than or equal to 1. Greater than or equal to 1 because our first term is 1/2. And then we already identified the first term, the second term, the third term, and so on. Okay, so in other words, our n should be greater than or equal to 1 because there's no such as n equals -1 or 0 in this case. So, in other words, our uh, a sub n plus 1 minus a sub n is greater than 0. Why? Because if we are going to substitute any number greater than 1, let's say just greater than or equal to 1, let's say 1. So that is 1 all over 1 squared plus 3 times 1 plus 2. So that is greater than 0. Therefore, this proves, therefore, we could now say, where is my cursor? Therefore, we could now say that uh, okay, Therefore, we could say that 1 over n plus 2 times n plus 1 is greater than 0. Okay, because if we are going to substitute any number here greater than 1 or even equal to 1, that's always greater than 0. So by the concept of the differences of successive terms, this is greater than 0. Therefore, we could say that uh, the sequence is strictly increasing. Okay, next, use the ratio of successive terms so that to show that the sequence is strictly increasing. So same, what we're going to have. Okay, in this case, our a sub n would be n over n plus 1, and our a sub n plus 1 is equal to, same with what we did in the other slide, that would be n plus 1 all over n plus 2. Now take note that we are going to use the ratio of successive terms. Then we could have uh, a sub n plus 1 over a sub n, which is equal to, you have n plus 1 over n plus 2 all over n plus 1. In this case, then we have n plus 1 all over n plus 2 multiplied by the reciprocal of this one. So that would be n plus 1 over n, which is equal to n squared plus 2n plus 1 over or all over n squared plus 2n. Okay, in this case, if we're going, take note that our n is greater than or equal to 1. So if we're going to substitute 1 in the given equation, so that is 1 squared plus 2n plus 1 all over n squared plus 2n, so that is 1 plus 2 plus 1, which is equal to 4, because 1 plus 2 is 3 plus 1 is 4. Tapos 1 squared plus 2, that's equal to 3. So 4 over 3 is always greater than 1. Okay, so this proves that the given sequence is increasing. Okay, properties that holds eventuality, or eventually rather. Okay, so in this case, we have our definition. Okay, sometimes the sequence will behave erratically at first and then settle down into a definite pattern. Okay, so uh, in this case, to describe a pattern that is that holds eventually, then let's have this definition. If discarding the finite many terms from the beginning of the sequence produces a sequence with a certain property, then the original sequence is said to have that property eventually. Okay, so let's have an example. Show that the sequence uh, n raised to n over n factorial from 1 to positive infinity is eventually strictly decreasing. Now, to have that one, uh, okay, so in this case, if we are going to identify the elements, okay, so if n is equal to 1, then that is uh, 10 raised to 1 all over n factorial, which is 1, so that is 10. Okay, and then if that would be 2, that is 100 over 2, so that would be 50. So this at first the sequence is erratic because of the presence of the denominator, which is n factorial. So let's have our solution to this problem. Okay, so let's have, so for our solution, okay, let's use the uh, ratio. Okay, so our a sub n is equal to uh, 10 raised to n all over n factorial. And our a sub n plus 1, or the next term, would be, you have uh, 10 raised to n plus 1 all over the quantity n plus 1 factorial. So if we are going to divide that one, then you have uh, a sub n plus 1 over a sub n. That would be equal to, uh, you have 10 raised to n plus 1 over uh, the quantity n plus 1 factorial all over 10 raised to n over n factorial. Okay, so we can have the multiplication. Okay, you have 10 raised to n plus 1 over the quantity n plus 1 factorial multiply by n factorial over 10 raised to n. In this case, then, since both numerator and denominator has the base of 10, then uh, we can have the uh, factoring by removing common factors. So that would be, in this case, you have 10 times, you have n factorial over n plus 1 n factorial. Okay. In this case, then we can now divide out the n factorial. So divide out the n factorial. So you have 10 over n plus 1. Okay. So if our n is greater than 10, because at that case, then um, there would be uh, greater than 10, because there would be a factor of 10 within the n factorial. Take note, if n is 1, then you have 1 factorial. If n is 2, then 2 factorial, and so on. So when you reach the value of 10, okay, any number of n that is greater than 10 or greater than equal to 10, all of them has a factor of 10. So we can now, there would be now a pattern. So in this case, uh, if n is greater than 10, greater than or equal to 10, then for all, the sequence would be eventually strictly decreasing, as this is as uh, the value of the ratio between the terms, the succeeding terms, kanang shows. Okay, so that's for this reason, then we could have, okay, therefore, oops, that must be therefore. Let me correct first. Therefore, okay, the sequence 10 raised to n over n factorial Ah, from 1 to positive infinity is eventually decreasing rather, decreasing. Okay. So, an intuitive view of convergence. So, informally stated, the convergence or divergence of a sequence does not depend on the behavior of its initial terms, but rather on how the terms behave eventually. So, for example, we have this uh, sequence, you have 3, -9, -13, so on and so forth. Okay, eventually behaves like the sequence 1, 1/2, 1/3, and so on up to 1 over n. So hence, in this case, the limit of the sequence 3, -9, 1/3, 3, -9, -13, 17, 1, 1/2, 1/3, 1/4, and so on. Okay, has the limit of 0. Okay, so let's have convergence of monotone sequence. So the following, um, the theorem, okay, will show that the monotone sequence either converges or become infinite. Divergence by oscillation cannot occur. Okay, so let's have this theorem. If the sequence is eventually increasing, then there are two possibilities. One, there is a constant number m called the upper bound, such that the a sub n is less than or equal to m for all n, in which the case the sequence converges to the limit L, satisfying L less than or equal to m. And uh, no upper bound exists in the case the limit of the sequence as n approaches to positive infinity is equal to positive infinity. Okay. Okay. Another theorem, if the sequence is eventually increasing. Okay. That's not increasing, that is decreasing. Sorry. That would be decreasing. If the sequence is eventually decreasing, okay, let me correct it first. There are two possibilities. There is a constant m called the lower bound, such that the m sub n is greater than or equal to m for all n, in which case the sequence converges to the limit L satisfying L greater than or equal to m. And the second possibility would be no lower bound exists in which the case the limit of a sub n as n approaches to positive infinity is equal to negative infinity. Okay, so let's have this one as an example. Show that the sequence uh, n raised to n, 10 raised to n over n factorial from 1 to positive infinity converges and find its limit. So let's have the solution. Okay, now the sequence is eventually decreasing or eventually strictly decreasing as shown in the previous example. Since all terms in the sequence are positive, it is bounded below by m equals 0 because all of them is positive, and hence it guarantees using the second term that it is converges to a non-negative limit L. However, the limit is not evident directly from the formula, n raised to n all over n factorial for the nth term. So we will need some ingenuity to obtain it. So in this case, let's have the successive terms. Okay, so we are going to use in this case that our a sub n plus 1 is equal to 10 over n plus 1 times a sub n. How come? Okay, for those who are asking, if we're going to review, we have a sub n plus 1 over a sub n is equal to, you have 10 over n plus 1. Cross multiplication, then you could have this answer above. Okay, so here our a sub n, okay, equals n raised to n over n factorial. Okay, so in this case, we'll take the limit as n approaches to positive infinity of both sides of the equation. So to use the fact that, then, okay, we have, okay, so in this case, then we get the limit of both sides, then we have the limit of uh, a sub n plus 1 as n approaches to positive infinity is equal to uh, the limit of a sub n as n approaches to positive infinity, which is equal to our L. Okay, in this case, uh, we could obtain that our L, okay, our L would be equal to the limit of a sub n plus 1 as n approaches to positive infinity, okay, which is equal to the limit of, okay, substitute this one, you could have 10 over n plus 1 times a sub n as n approaches to positive infinity. Okay, then we could have, okay, what will happen is we can use the product. So you have the limit of 10 over n plus 1 as n approaches to positive infinity times the limit of a sub n as n approaches to positive infinity. Okay, so you have n approaches to positive infinity. Okay, which is, if we are going to substitute the n to positive infinity, then the limit of this one is equal to 0. So this case, if we are going to substitute this one, is equal to 0. So the limit of this one as n approaches to positive infinity is equal to 0, okay, taken from your previous calculus, multiplied by, we know that the limit of a sub n as n approaches to positive infinity is equal to L. Therefore, this is equal to L. Okay. And in this case, we could say that our L, okay, our L, which is the limit of 10 raised to n over n factorial, okay, as n approaches to positive infinity, is equal to 0. So in this case, we could have that eventually, okay, uh, the the limit of the sequence is equal to 0. Okay, so let's have completeness of action. Okay, so for the completeness of action, in this presentation, we have accepted the familiar properties of real numbers with a proof, and indeed, we have not even defined it in the real term. So, although this is sufficient to many purposes, it was recognized by the late 19th century that the study of limits uh, and functions and calculus requires a precise axiomatic formulation. So in this case, let's have the axiom, the completeness axiom. Okay, if the non-empty set S of real numbers has an upper bound, then it has a smallest upper bound, which called the least upper bound. And if the non-empty set S of real number has the lower bound, then it has the largest lower bound, which is called the greatest lower bound. Okay. So let's have this infinite series. Okay. So for the infinite series, we are going to talk about uh, some uh, concepts. Okay. In uh, let's say non non-terminating fractions or non-terminating numbers. Okay. So let's have these taken from the completeness axiom, the infinite series in an expression that can be written in the form of the summation of u sub k from 1 to infinity, which is equal to u sub 1 plus u sub 2 and so on. The numbers u sub 1, u sub 2, u sub 3 are called, of course, terms in the series. Okay, so let's have this one. Okay, so let s let the sequence, not the sequence, the set of sequence to be a sequence of partial sums in the series. So uh what will happen? So you have u sub 1 plus u sub 2 up to u sub k and so on. If the sequence converges to a limit s, then the series is said to be convergence to s, and the s is called the sum of the series. We denote by the writing um, S is equal to the summation of u sub k as from 1 to positive infinity. If the sequence of the partial sums diverges, then the series is said to be diverge. A divergent series has no sum. Yeah, okay, so let's have this one as an example. So determine whether the series 1 minus 1 plus 1 minus 1 plus 1 converges or diverges. So in this case, let's have an example. Okay, now if it converges, find the sum. Okay, so the solution of this is uh, we are going to it is tempting to conclude that the sum of the series is zero by arguing that the positive and negative numbers cancel one another. However, it is not correct. The problem is algebraic operation that holds the finite sum do not carry over to infinite series in the sequence or in all cases. Okay, we are going to discuss some of the familiar algebraic operations that can be applied to infinite series. But for this example, we will turn directly the definition the partial sums. Okay, so in this case, so let's say the sum of the first term, okay, we could have our s, okay, take note, s sub 1 is equal to 1, s sub 2, the sum of the two terms would be 0, okay, the sum of the three terms is equal to 1, the sum of four terms is equal to 0, and so on. So thus the sequence of the partial sum is 1 0 1 0 1 0. So in this case, the partial sum is 1 0 1 0 1 and so on. Okay, so since this is the sequence of the sum, then this is divergent sequence because the sum is 1 0 1 0 1 0. So it does not arrive to a certain limit. Okay, so in this case, therefore, okay, we could say that um, the sequence diverges. Okay, the sequence diverge because the partial sum, has uh, is not converging to a certain number. So this is the explanation why this sequence 1 negative 1 plus 1 minus 1 plus 1 minus 1 plus 1 and so on is divergent sequence or sum. Okay. So geometric sequence. Okay, in the geometric sequence, the sum, the summation of a r raised to k from 1 to positive infinity is equal to a plus a sub ar plus ar squared and so on to a r raised to k, where a is not equal to 0. Converges if the the absolute value of r is greater than 1, and if diverge if the absolute value, okay, of r is greater than or equal to 1. Okay, so take note, it converge if the absolute value of r is less than 1, and if it diverge if the absolute value of r is greater than or equal to 1. If the series converges, then the sum, okay, would be equal to a over 1 minus r. Okay, so let's have an example in this case. So you have determine whether the series converges, and if so, find its sum. Okay, now take note, we have the first one. You have the 5 over the summation of 5 over 4 raised to k from 0 to 1. In this case, this is a geometric series with a is equal to 5, okay, and our r is 1/4. Okay, so we could have this one. Okay, so for our solution here, we could have our uh, our a is equal to 5 and our r is equal to 1/4. So clearly our r is less than 1. Okay, so since the absolute value of r is equal to 1/4, which is less than 1, then the series converge. Okay, therefore the series converge. So the series converge. Okay, and since it is the series converge, then the sum. Okay, the sum would be, take note, because we're talking about the sum if it converge. So the sum of 5 over 4 raised to k, k equals 0 to infinity, that would be equal to our formula, a over 1 minus r. So that would be 5 over 1 minus 1/4. So that would be equal to 1 minus 1/4 is 3/4. So 3/4, that would be equal to 20 over 3. Okay, so the sum would be equal to 20 over 3. Okay, so let's have another example. So determine whether the sequence or the series rather converges. If so, find the sum. For this example, we could have the geometric sequence or series is in the concealed form. So since it is in the concealed form, we can rewrite this one. Okay, let's try to rewrite. Okay, we could have we can rewrite this one as uh, the summation of uh, the summation of how to so take note 3 raised to 2k, that could be written as uh, 3 squared k. So you could have 3 squared is 9 raised to k. And since this one, uh, you have 1 minus k, or we could factor the 1 minus k, removing the negative, so that would be negative quantity k plus 1. So if it is negative, then we can write this one in the denominator. So 5 raised to k minus 1 from 1 to infinity. Okay, so it is much more clear now. So in this case, we could have since you have 9 raised to k, so again the 9 raised to k, we can actually remove the 9 there. So it could be the summation of 9 times, you could have uh 9 raised to k minus 1, because because the exponent of 9 is 1. So if we are going to add to multiply the same base, we are going to add the exponent. Okay, over 5 raised to k minus 1 from k equals 1 to positive infinity. So in this case, we can rewrite this one as the summation of 9 times 9 over 5 raised to k minus 1 from 1 to positive infinity. Okay, so we already have this one. And as we can see also here, we could have from here, we could have that our r is equal to 9 over 5, which is okay. If we are going to get the absolute value, the absolute value of this, okay, absolute value of r, this is greater than 1. And since the r is greater than 1, then we could say that the series diverges. And if the series, this is D. If the series diverges, there is no sum at all. Okay. So let's have example 8. Find the rational number represented by the repeating decimal. You have 0.7847, and so on. So for our solution, we can rewrite this one. Okay, we can rewrite okay the okay the fraction or not the fraction, the decimal. So you have, let's say we are going to equate we're going to equate this one. Okay, we're going to substitute that one as d. So our d, okay, would be equal to, you have 0.784 plus 0.123784 plus 0.123456 plus so on. Okay. Now in this case, our this one, okay. So since you have this one, the D, okay, we could have the given decimal is the sum of the geometric series, okay, where our A would be 0.784 with R, okay, take note as you can see here, right here, okay, uh, we could have uh, the our R would be 0.001, okay, so we could have uh, D, okay, is equal to A over 1 minus R, where our A would be 0.784 over 1 minus R, which is 0.001, because the common factor here is 0.001. Okay, so in this case, that would be equal to, okay, 700, uh, not 700, 0.784 over 0.999, which is equal to 784 over 0.999. So the rational number that represents the repeating decimal is 784 over 999. So take note here, our first term, okay, the first term in the sequence would be 0.784, and the common ratio, okay, if this would be the series, if this would be the sequence, okay, the sequence, if this would be sequence, then the common ratio, okay, between those numbers would be 0.001. So that would be the process. Okay, so let's have this one. Find all the values of x for which a series converges, and find the sum of the series, okay, of for those values of x. So here we can expand our solution. So for the given, we can expand. Where is my cursor? Okay. So in this case, we can expand. This could be written as the summation of uh, x raised to k from 0 to infinity, as you could have uh, x raised to 0 is 1 plus x plus x squared plus so on plus x raised to k plus so on. So in this case, we can see that it is a series of, it's a geometric sequence or geometric series rather. So in this case, our first term is 1. Okay, and of course, our R would be x. That's the common ratio. So uh, So if our r, okay, our r is equal to x, we know that, okay, this implies that if r, this absolute value of r, okay, not the absolute value of, it must be the absolute value of x, rather, well, anyway, it's the same. It's just equal to the absolute value of x should be less than 1, okay, and it diverge otherwise, okay, then the series converge to the sum, okay, if this is convergence, okay, if this converge, then the sum of uh, x raised to k from 0 to positive to infinity would be equal to 1 over 1 minus x. Okay. So in this case, this is arbitrary because we do not know yet the value of our x here. So the if the absolute value of our x is less than 1, then it converges. Otherwise, it diverges. So since there's no number yet, okay, in our x, then if we are going to assume that this absolute value of r, okay, is less than 1, then it is convergence. It converge. Okay. Determine whether the series below converges or diverges. If converge, find the sum. So in this case, okay, in this case, uh, we could rewrite this one, okay, as we could observe what happened. Uh, okay. Hmm. So let's have the nth partial sum of the series. Okay. So you could have, in this case, you have, uh, we will begin by rewriting the series, the sum, okay, in a closed form. This can be accomplished by using partial fractions. Okay, so in this case, using the partial fraction, we could have the 1 over k. So that would be k. What happened? Okay, so using the partial fraction, then we have this one. Okay, I believe that partial fraction is discussed to you in the previous calculus. So that would be 1 over k minus, we could have 1 over k plus 1. So that would be our uh, partial fraction. Okay, so from which we can obtain, okay, using the concept, using the same concept of the sum, you could have, okay, the sum, the s sub n, that would be equal to, okay, the summation of the partial fraction, okay, 1 over k minus 1 over k plus 1, this is k, from 1 to infinity. Okay, that would be the same as, you could have 1 plus 1/2 plus, because it's a series, so on. Then we could have, okay, to conserve the space, then you could have 1 over n minus 1 over n plus 1. Okay, so in this case, okay, uh, uh, since it is a fraction, we can actually rewrite this one. Okay, in this case, we can take note that mm, this is 1 plus, not plus, it must be minus 1 minus 1/2. This is minus because on the formula you have 1 over k minus 1 over k plus 1. This is k plus 1. Okay, so this is 1 minus 1/2. Then you could have 1/2 minus 1/3. Then uh, you could have 1/3 minus 1/4. Then we could rewrite this one because the next number here is 1/2 minus 1/3, then 1/3 minus 1/2. So we could rewrite this one as 1, okay, plus you could have uh, the next term of this is 1/2 minus 1/3. So you could have 1/2 minus 1/2. Okay, this first 1/2 is taken to the from the next term, 1/2 minus 1/3, and then minus 1/2 plus. Okay, what remains is, here you have negative 1/3, but you have positive 1/3 in the next term, so you could have 1/3 minus 1/3 plus so on up to the sequence. Okay, uh you have negative 1 over n plus 1n, 1 over n rather, okay, minus 1 over n plus 1. Okay, so in this case, okay, this would be equal to 0, 0, 0, 0. What remains is you have 1 minus 1 over n plus 1. Okay, so um, getting the limit, okay, so the limit, okay, of the s sub n as n approaches to positive infinity, so this is equal to the limit of 1 minus 1 over n plus 1, okay, as n approaches to positive infinity. So in this case, okay, the limit of 1 is 1, and then here minus the limit of 1 over n is equal to 0. Therefore, you could have 0, not 0. That would be 1 plus 0. So as I said, the limit of constant is constant. So the limit of 1, so here the limit of this one, okay, is 1 minus the limit of this is 0 is equal to, okay, 1 minus 0 is equal to 1. Therefore, the limit of the sequence is equal to 1. Okay, so harmonic sequence. Okay, one of the most important of all divergence series is the harmonic series. So this would be the harmonic series, okay, which arises in connection with the overtones produced by vibrating musical strings. Okay, so it is not immediately evident in the series of divergence. As we can see, it's not immediately evident that this series diverges. However, the divergence will become apparent when we examine the partial sum in details. So, because the terms of the series are all positive, then you could have the partial fraction. So, if the in this case, let's say the first series, okay, if the series is one, the sum of the first is one, then the sum of the second two terms, the first two terms, is equal to one and one half. Okay, one plus one half, and then the third series would be one plus one half plus one third, and so on. Okay, so in this case, you could have, okay, the first series is less than the second series, which is less than the third series, which is less than so on up to the series. Okay, which is, I guess, this the same. Okay, now thus, okay, using the theorem, we could say that this is diverged by demonstrating that there is no constant m that is greater than or equal to every partial sum. So to this end, we will consider some selected partial m's. So let's have s sub 2, s sub 4, s sub 8, s sub 16, s sub 32, and so on. So note that the subscript of the successive powers is 2, so that these are the partial sums of the form s of base 2 raised to n. Okay, so in this case, uh, if our first s sub n, okay, would be 2, okay, then we are going to have the s sub 2 is equal to 1 plus 1 half, which is greater than 1 half plus 1 half, which is equal to 1. Okay. And then you could have S of 4. So for the S of 4 is equal to S of 2 plus 1/3 plus 1/4, which is greater than S of 2 plus 1/4 plus 1/4, which is equal to S of 2 plus 1 half, which is greater than 3 halves. Okay. If you can notice that there's no such there's no such all of the sequence in the series, the sum is there's no constant m. Okay, therefore this there's since there's no constant m, then this is a this proves that the harmonic sequence, okay, we will end this one in this case, because if this would be s sub 8, then you could have s sub 4 plus 1, that is greater than 2 halves, or 4 halves rather, or which is 2. Then s sub 16, you have 8 1 6. Okay, okay, okay. So that would be s sub 8 plus 1 half, that is greater than 5 halves. So there's no constant m in each partial sums. Therefore, this proves that the harmonic sequence sequence diverge. And since it diverge, then there's no sum. Okay. So let's have convergence test. For the convergence test, um, we have shown previously how to find the sum of the series by finding a closed form for the nth partial sum and taking its limit. However, it is relatively rare that one can find a closed form for the nth partial sum of the series. So alternatively, the methods are needed to find the sum of the series. One possibility to prove that the series converges and then to approximate the sum by partial sum with sufficiently many terms to achieve the desired degree of accuracy. Okay, so let's develop various tests that can be used to determine whether the given series converges or diverges. Okay, so let's have divergence test. So you have in stating the general results about the convergence or divergence of series, it is convenient to use the notion or the notation summation of u sub k as a generic notion for a series. So to avoid the issue of whether the sum begins with k equals 0 or k equals 1 or some other values. Indeed, we will see shortly that the starting index value is irrelevant to the issue of convergence. So the kth term in the infinite series, the summation of u sub k, is called general form of the series. So this would be the theorem. Okay. So if the limit of the u sub k, okay, as k approaches to positive infinity is not equal to 0, then the series diverges. If the limit, okay, of u sub k as k approaches to positive infinity is 0, then the series, okay, may either converge or diverge. If the series, okay, as u sub k approaches to positive infinity converges, then the limit of the u sub k is equal to 0. Okay, so let's have an example. In this case, show that the series below diverges. Okay, so you have the summation. Okay, so to answer this one, let's get the limit. Okay, the limit for the solution, what we're going to do is we find the limit of k over k plus 1 as k approaches to positive infinity. So in this case, okay, we have to uh, divide by k. So if we are going to divide by k, so if we are going to divide our numerator and denominator by k, so you have the limit of 1 over 1 plus 1 over k, k as k approaches to positive infinity. Then you have, of course, the limit of 1 is 1 over the limit of 1 is 1 plus the limit of this one is 0. So you have 1. And of course, 1 is not equal to 0. So by theorem, okay, if the limit is not equal to 0, then it diverge. Okay. Algebraic properties of infinite series. So you have here theorem. Okay. So if the series, okay, two series are convergent series, then the sum, okay, and uh, this is the sum of the two series and the difference of the two series are convergent series, and they are related by this one. Okay, so the you have that one, you have the summation of the quantity u sub k plus v sub k from 1 to positive from 1 to infinity. Then you have the sum, then you have the difference, and then we have, if c is non-zero constant, then the series u sub k and c times u sub k both converges or both diverge. In the case of the convergence, the sum is related by this one. Okay. Then you also have is unaffected by deleting the finite number of terms from the series. In particular, for the positive integer k, the series k are both converge or diverge. Okay, for example, they have this one. Find the sum of the series. Okay, so you have this one. So what will happen? So as you can see here, uh, the first, okay, using the concept of the theorems for our solution, okay, we could have the series of 3 over 4 raised to k from 1 to infinity. Okay, that would be equal to 3 fourths plus 3 over 4 squared plus so on. Okay, now this is convergent. Why? Because if this is geometric sequence, geometric series, our A is equal to 3 fourths, then our R is equal to 1 fourth. So the sum, okay, would be taken from the formula. Then we could also have, okay, the series, the second series, okay, the summation, okay, of 2 over 5 raised to k minus 1, k equals 1 to infinity. So that is equal to, that would be 2, 1, 2 plus 2 fifth plus 2 over 5 squared plus so on. Okay, so this is also convergence. Okay, because it is a geometric series. Okay, for this case, okay, for this case, we could have our A here is 2 and our R is equal to 1/5. Okay, so by this case, then we can get the the sum. Okay, so and the difference rather, so you have this one raised to k minus 2 over 5 raised to k minus 1, k 1 to infinity is just equal to the summation of 3 over 4 raised to k from 1 to infinity minus, you have the summation of 2 over why 2, that must be 5. So in this case we have The sum of this, that would be our uh, A is 3/4. Then over, you have uh, 1 minus the R, which is 1/4, minus the sum of this. You have A is 2 over 1 minus 1/5. So here, this is 1 minus 1/4 is 3/4. 3/4 over 3/4 is equal to 1. Okay. Minus here, 1 minus 1/5 is equal to 4/5. So if this is 4/5, okay, divided by 4/5, so that is 2 times 5 over 2. So that is, uh, we have 5 over 2, and 1 minus 5 over 2 is equal to, this will become 5 over 5. Ah, you could have 2 over 2 over 2, so that is negative 3 over 2. Therefore, this is equal to negative 3 over 2. Okay. So let's have integral test. The theorem, integral test. Let the summation of u sub k be a series of the positive terms. If f is the function that is decreasing and continuous on an interval half open a to positive infinity, and such that the u sub k is a function of k for all k greater than or equal to a, then you have the summation of u sub k, okay, from 1 to positive infinity, okay, is the integral of f sub, integral of the function, f of x dx, okay, from a to positive infinity, both convergence or both divergence. Okay, so let's have an example. Show that the integral test applies. Use the integral test to determine whether the following series converge or diverge. So in this case, okay, we already know that this is a divergent harmonic series, okay, from the previous example. So the integral test will simply illustrate another way of establishing the divergence. Note first that the series has positive terms, so the integral test is applicable. If we replace k by x in the general term 1 over k, we obtain the function. So in this case, if we are going to replace this one, we obtain the function f of um, x is equal to 1 over x, which is decreasing and continuous for x greater than equal to 1, which is the requirement to apply the integral test with a equals 1. So in this case, we have uh, the integral of 1 over x dx from 1 to positive infinity. Okay, is just, okay, let's try to get the limit. Okay, so you have the limit of the integral, okay, 1 over x dx from 1 to, let's say, b, would be equal to the limit of, you have the natural logarithm b minus the natural logarithm 1, okay, as b approaches to positive infinity. In this case, clearly this is equal to positive infinity. Okay, so the integral diverges, and consequently, uh, so does the series. Okay, let's have uh, another s- another series. Note that the first series has positive terms, so the integral test is applicable. Okay, if we replace k by x in the general term, so what we have is you have a function. In this case, you have a function of x which is equal to 1 over x squared, which is decreasing, of course, and continuous for x greater than or equal to 1. So since we have this one, then we could have uh, the integral of 1 over x squared dx, okay, from 1 to positive infinity, okay, can be written as the limit, okay, of uh, dx over x squared from 1 to b as our b approaches to positive infinity, which is just equal to, here we have, okay, we have the limit, okay, of, you have negative 1 over x, okay, as b approaches to positive infinity, okay, from 1 to b, which is just equal to, okay, the limit, if we're going to get the subtract, if we're going to subtract this one, okay, which is equal to the limit of 1 minus 1 over b, okay, as b approaches to positive infinity. In this case, okay, the limit of constant is 1, the limit of this one is 0, so that is 1 minus 0 is equal to 1. So so in this case, the integral converges, and consequently, the series converges by the integral test with a equals 1. So since it's not equal to, okay, in this case, since the limit is equal to a number, then the integral, therefore, okay, the integral convergence, the integral converges. What happened to my pen? So we can say that the integral converges. Okay. So we have P series. Okay. Convergence of P series. So we have the summation of 1 over k raised to p as from 1 to from 1 to infinity is equal to 1 plus 1 over 2 raised to p plus 1 over 3 raised to p, and so on, converges if p is greater than 1, and diverges is if p is less than, if p is greater than 0 but less than or equal to 1. Okay, so let's have an example. So determine, okay, uh, determine if whether the following series converge or diverge. So in this case, uh, in the P series, uh, clearly this is using the concept of the P, okay, series. P is one third because the index of, okay, here, the index here is one third. So our P is equal to one third, which is less than less than 1. Okay, and since the p is less than 1, okay, but greater than 0, then the series diverges. Okay, so You have here if the series, if the summation of u sub k is a series with the non-negative terms, and if there is a constant, okay, there's a constant m such that the series is equal to u sub 1 up to u sub n less than or equal to m for every n, then the series converges and the sum s satisfies n less than m. If no such m exists, then the series diverges. Okay, so that's the theorem. Okay, in the next discussion, we are going to talk about more on this. So I guess that's all for this presentation. Thank you.